All right, thanks for coming to the Applied Math Colloquium. We're delighted to have Rick Johnson today from Electrical and Computer Engineering. He, I believe, I actually should have checked with you, has a master's in art history, is that true?
A PhD minor.
A PhD minor
Yeah.
in art history, in addition to being an expert on signal processing. So I think you'll see both of those interests in today's talk, which is about computational art history. Thanks for coming.
Thanks, Steve. So I guess I should start by apologizing. I don't have any equations in the slides.
Oh.
I know this is a grave disappointment, and I almost wasn't going to mention at the beginning, just apologize at the end, that I forgot. But it's kind of on purpose because actually the level of mathematics I'm going to be talking about is very low. It's low enough, in fact, that the topics were chosen in part because I wanted to be able to involve undergraduates in actual research projects, solving problems where the answers aren't already known and trying to give them a sense of the excitement of some of the things we do, and which is very hard to do. Normally they get to stand and watch you do research, but they don't really get to participate. Also, it was because I was bridging between two fields that are as far apart as one could imagine. If there were anything that you thought might not lend itself to, shall we say, deep insight due to applied mathematics, something like art history would come to mind. I'm sure you've all heard, I think it was Obama actually, when they were talking about, useless degrees. Okay, art history was the one that came up. Okay, so I mean, I can't remember. It may have been one of the administrative officials, but so I guess the interesting story would be to tell you how I got there, but that's not what I'm going to do. I'm going to take a more standard route and tell you what I saw once I got there. But a little bit about how it happened is useful, and that is this is the second time I've changed my research direction in my career. If you're lucky enough to pick one topic area and have it sustain you through your whole career, consider yourself extraordinarily lucky. Okay, and so this time when I changed, rather than picking something because the government was willing to provide lots of money, or students really, really wanted to work in that area, or any of those things that we often normally choose research problems for, I decided to choose something that I was emotionally involved with, and which is the art history subject, and that did not come about because of some natural thing when I was young. I didn't go to a museum until I was in my early 20s. I grew up in the Deep South, and in my cultural background, going to a museum was just, I take that back. The space in the Air and Space Museum in the Smithsonian, that's okay. Okay, that's the kind of museum. But art museum just wasn't in the cards until I had a fellowship overseas as an undergraduate, and it was an experience that changed my life. So I went into my first museum and ended up spending a few hours in the room with the Rembrandts, not understanding what had happened to me. And then I got to grad school, and I spoke with some of the students earlier at lunch and told them part of the story. I arrived to Stanford at a time when if you made below a C on a course, they erased it from your transcript, which was beauty. It meant you could take anything, you didn't have to worry about anything, because we all know how to fail. You just walk out of the exam, the final exam, without doing anything. That'll usually gather you an F. Okay, so I felt, right, how can I lose? And so I talked my way into my first art history course was a graduate level symposium on Rembrandt, and I was the dumbest thing in the class, dumber than the furniture. Okay, I mean, I asked incredibly stupid questions. I was really fortunate to have fallen in with some faculty who were quite willing to. Now I know why they needed the extra body for the body count. Okay, but it was a real balancing experience while I was a graduate student between the way things were done in engineering and the way they were done over in art history. And I ended up taking so many courses that with my mentor, we decided it might not be a bad idea to see if we could get something on the record about this. So that's where the PhD minor came from. And then 30 years, you do all the things you have to do to be an engineering professor. Okay, and so then I come to my second change in direction. And so I was actually on a Fulbright in Paris and made some connections with somebody through the Van Gogh Museum, had a meeting with the Van Gogh Museum, and actually within a few months they had agreed to sponsor the first workshop on image processing for artist identification, which I founded and created and so on and so forth. And that was my Trojan horse. I had no intention of actually doing authentication, because the first rule I learned is when you're trying to start an interaction or research, don't pick a problem to which that field can't agree on the answer. So what you wanted to do was find something where everybody already agreed, but it was too odious to do manually, and then in comes the computer. Okay, and once the camel's nose is in the tent, you can do all kinds of fancy things. So basically that was the idea. I organized this workshop, brought people together, and got to stand around and listen to everybody. Spent about 18 months going back and forth to the Netherlands about every 2 months or so. I was self-financed, so nobody would pay for this, and it's a field that didn't exist at the time. And during that time, we found the first problem that turned into a really neat computational task to do something they already wanted to do. And by the time these are all the things we know, by the time you could do it to the scale that the computer would allow you to do, the thoroughness, you began to see things that nobody had realized was actually there until you thought about it, and then it made sense. And it turned into really terrific tools that we were not looking for. In other words, it had all the hallmarks of what you call basic research. So I had to learn a lot of things about how to deal with people that don't speak mathematics. This is why it's fun to talk to you guys. So imagine trying to describe to people that literally don't speak mathematics at all. When I was in grad school, some of the professors in art history bragged about how they couldn't do arithmetic and balance their checkbook, and this was a badge of honor that they couldn't do any simple mathematics. Okay? And whereas if I had told them Shakespeare, you got to be kidding, what trash, I'd never read that stuff, I would immediately be branded as subhuman. So somehow there's this whole cultural divide that you also have to learn your way around. And as computers and applied math find a larger audience of problems, and they're out there in the areas you haven't looked yet, part of the way of bringing it forward and making it happen will be that you learn how to interact and talk to people that can't speak math and understand what they're trying to do in a way that you can convert it to your language and actually help them. So I had a bit of advantage because that's the way I pitched myself first. How do I go to somebody who's already working with the Van Gogh Museum and say, I'm here to figure out what you're doing so I can do it instead of that works really well, doesn't it? Okay. So basically I tried, because I didn't really know. The person I'm talking to that got me in the door was a computer science, okay? And he does AI, machine learning types of things that I'm not expert in at all. And so it clearly wasn't the case that I was going to try and take, but I wanted to know how things are going. They weren't going well. So I said, well, look, I can talk to both sides. I'll try to be a translator. So that was my first pitch, was I'm going to help both of you if I talk to each other and figure out what's going on. And I got to give the Van Gogh Museum a big gold star, because at the very first meeting that I had with the executive types, the head of collections, the head of research, and the head of conservation, they agreed at the meeting, this is the Dutch for you to some extent, they said, please step outside for 2 minutes. I come back, everything's agreed to, they're willing to be the sponsor. Okay. And they were great. And they allowed me to come every couple of months and sit with their head of paintings conservation. And we went through a bunch of problems. I got to hold the paintings. I got to take them out of the frames, wore the little gloves, and, it was fabulous. It was just fabulous. Okay. So what did we find? That's what the talk's going to be about. So what I'm going to tell you is not what I was thinking then. I could go back and do some of that, but I'm going to tell you the way I see it now. So I'm going to tell it to you like you would read it in a book, rather than the history. It's going to be the pedagogy of what. So what do art historians care about? Are there any? I should ask. Any art historians? Oh, good. I have to be careful what I say about art historians. How about computer scientists? People from the CS department. Oh, good, we can slag computer science. That's good, okay. Applied mathematicians, that ought to be everybody else, right? Okay, so from my perspective, the thing art historians care about, of course, is they want to understand the stylistic development of artists, how they influence each other, all these things that seem outside of our realm, so how can we contribute? But the thing they need is they need to know what order the artworks were produced, and who did what. They can't, in other words, if you sprinkle a few fakes in somebody's catalog, then your in conclusions about what's going on will be wrong. If you take the dates and scramble them a little bit, your understanding of the progression of the artist over their career is going to be full of holes. It's going to have, so one of the things they care about is getting a full chronology that has everything with the right dating. Okay, and so it turns out that one way to help that, and one way that's been done, but only probably really seriously in the last 20 to 30 years, is to look at the materials of the object and to try and compare the materials in an object that you know and show that identical materials were used in a second object that you're trying to test. And this can help you put them in, arrange the ordering and stuff. Well, it sounds a little vague at that point, which it should. And it turns out this sort of physical evidence is really only one piece. Okay, so they've got to know the provenance of the art, so that's the documentation about it, who's owned it over the years, what the style of the brush strokes. In other words, most connoisseurs, most art historians will tell you they can identify the artist by seeing the hand of the artist in the painting. In other words, like the brushwork is like a signature. Okay, this becomes a fairly difficult thing to get the computer to do because the art historians can't agree whose signature it is. So even if I tell them the answer, only a part of them are going to agree that I've got it right. So this is not a great way to convince the community. But there's brushwork, composition, documents, other materials like the paints and ground layer and stuff. But it seems pretty straightforward when you think about it that most of the materials that art is put on, and I'm going to talk just about canvas and paper, is a made material, and it turns out that these things often have patterns in them. They're not patterns that were there by design, but they're patterns because of the way the material was made. And it turns out if those patterns are somehow specific to each instance in which the material is made, then you can talk about materials that were made at the same time. Canvas made on the same roll, pieces of paper made with the same mold for handmade paper, or paper made on the same machine to the same chemical process if it's photographic paper. So that's a pattern. Signal processing, that's perfect. So I can use signal processing to extract the pattern from the image, quantify its description, characterize it in some way, pick out the features that matter to me perhaps, or in some cases the features are already told in advance what you're looking for, but somehow extract them automatically and compare them automatically and probably reduce the time commitment by a factor of 100 to 1,000 easily. Okay. Furthermore, you unleash something that wasn't there before. So a typical exhibition, if you go to a museum and there's some special exhibition, there's maybe 30 paintings. It's an enormous amount of work to get them ready for the exhibition. It takes 3 to 5 years to prepare an exhibition. All the paintings are cleaned and studied, and you have to arrange loans for the ones you don't have from other museums. And so there's several years in advance where they do a lot of scientific study, and during that period, they're looking at these things in great detail. So there's all this information that we would like to help by bringing to bear in this forensic analysis that allows them to say things about dating. Okay, so that's the scenario, is that I have this idea, and I'm telling you there's patterns in the material. You don't know about those yet, but there's patterns there to be found, and this is what signal processing can do. We all know this. So let's try to do that. And I think of this, if you want to use a really, I think, current buzzword, think of it as feature mining instead of data mining. And there are people actually like Serge Belanger who do things called feature mining, where in some cases you might not know the features you're looking for. We'll do one problem like that. In the others, you know the features you're looking for, and you're going to mine them, extract them, quantify them, and refine them, just like you might do fuel in order to drive some other process. So here's the 3 problems. The sabbatic I was on was in 2005. I made the pitch to the Van Gogh Museum in 2006, and the first workshop was in 2007. And by that time, that was when I actually did the first instance where I did what's called thread counting. And I'll tell you a lot more about that in a minute. So I started in 2007 with the Van Gogh Museum. And my idea actually was to have a set of problems, ultimately, that span some of the basic tools in image processing, because what I'd really like to do is write a textbook that both conservators and engineers could use, so that they start with the same language, and then they can collaborate with each other in the future. So very fundamental, but trying to imagine teaching image processing without math. Everybody, the blood should drain from your face at this point, right? Okay, and it actually turns out, I think, to be easy. We're still in the middle of trying to make it happen, but that's because if we talk to the art historians or the conservators, what they have is an incredible visual acuity. I mean, they're trained from day one to see patterns and to see, if you will, artifacts and images. They look at images all the time. So the idea is, can you visually communicate what image processing does? I mean, actually, it's trivial because the image is already visual. So the idea is, here's the image, I put it through box X, here's the image that comes out, and I swear to you, you do 2 or 3 of those with the art historians or the conservators, and they go, I know what box X does. And then the idea is to get them to see a sequence of boxes doing the thing you want to do to the image, and to start making them think like us. Algorithms, procedures, to capture, say, 90% of the standard problems, and the other ones are the fun ones, okay? So that's the idea. So that's for Old Master. Conservation. Turns out the field of conservation divides around 1900 into Old Master and Modern, and the two communities actually train slightly differently, and some of the problems that matter in one don't matter in the other. So the second problem I picked was more modern, and that was classifying photographic paper. As I'll point out later, photographs are now selling for $500,000 a piece and up. This is what, if you're a decamillionaire, you collect photos. If you're a billionaire, you collect paintings. So this is a new big thing where photos, and they have to be photographs made by the photographer, not by an assistant. They have to be developed by the photographer to carry that value. How do you know they were developed by the photographer? Well, you have one that you know is by the photographer that's on paper X, and I show you that this other one, that's the same image, is also on paper X. Okay, that's it. And that's done how? By looking at the texture of the paper. This is what they already do by eye. Okay, how many pages of paper, how many different kinds of paper are there? Over 15,000 during the mid-20th century when photography became an art form. So doing this by hand is out of the question, just out of the question. And of course, the people looking at them can't tell you what features they see. They can just, it's like pornography. I can't tell you, but I can tell you when I know it when I see it. Okay. So, and then, however, I was interested in Rembrandt, so I was always looking for a project with Rembrandt, and it turns out that Rembrandt's prints, okay, were made on what's called laid paper. Laid paper is the way paper was made until the mid-18th century, 1750s, like that. And it's a wooden frame with wires in the middle. It's like a screen. You dip it into pulp. The water drains. The pulp dries on the screen. You roll it off. That's a sheet of paper. And that's the way all paper was made, worldwide. And the problem is, or the issue is when the paper sits on the screen and dries a little bit, the screen makes an impression in the paper. And where the screen makes an impression, it's a little bit thinner than everywhere else. So if you hit it with a low energy X-ray, the parts that are thinner are highlighted in the image, and so you can see these features of the screen. The screens are handmade. They're all a little bit different. So the idea is, can you match them up? We find pieces of paper made on the same screen. Very simple. All of these, very simple. You just don't know they exist. It took me years to stand around with these people and finally find these pockets. They didn't know what skills I had. Does that make sense? Are there any questions so far? Once you've got your head around this, the rest of it's just fun. Okay? So, very, very straightforward. Okay, so these are X-rays. These are 2 centimeter square blow-ups of X-rays of canvas. These are the positive rather than the negative X-ray. And I dare say everybody in the room can see the canvas, right? Yep. Okay, you can see what looks like a simple over and under weave. You could count the number of vertical threads in the horizontal threads, and you would have what's called a thread count. Okay, and you can see that in some places it's not so easy. This interference, ugly, bad, terrible, horrible, meaningful. Why is it there? Interference. It's the artwork. If it weren't there, we wouldn't be here talking about it, right? So here's the thing, we're the good guys in the way, right? So we're trying to look at the canvas with the idea, what's the point? You count this, if you have 2 things that were made at the same time on the same roll of canvas, the idea is that anywhere you look, the average thread count's about the same. So the idea is if you have 2 pieces of canvas and they have different average thread counts, they cannot be from the same roll. Unfortunately, the converse is not true. They can have the same thread count and not be from the same roll. They're just made with the same thread count. Okay, so when I arrived at the field, so early to mid-2000s, all that was done was hand counting of a handful of spots, maybe 2 to 5 on a whole painting. You averaged those, and you got out your stats package and pushed the button, and you got the standard deviation and da-da-da-da. I'm kidding you not. Okay. And then you sat down and figured out which ones had averages close to each other. Okay. And then you said, well, maybe. And then you had to investigate a bunch of other things to go further, like the other materials that were used, et cetera, et cetera. Oh, and by the way, how do you count X-rays? I mean, how do you count the threads? I showed you this. None of this is on the computer. There's nothing that's been digitized. They have drawers and drawers full of X-rays on film. Why? Because when X-rays first came out, first invented, first discovered, one of the first things they were used on was paintings, because paint has lead in it. And what you could see is you could see beneath the surface. In other words, you could see where the artist had originally painted the arm this way, and then later had covered it up and painted it this way. And the art historians care about that, because this may have been modeled after some statue, and this is after a different one, or it has a different meaning, or it does something to the composition. So they, for a long time, had studied X-rays as a way to see what was happening beneath the surface. But then about the 1950s, some guys got the great idea that the thread count was related to the size of the canvas. So they did this great big study and discovered they were wrong. And so thread counting fell out of favor for a little while until the 68, 70, somewhere in there. And then there was something called the Rembrandt Research Project that was started. And this was a worldwide effort by a handful of Dutch experts to study every possible Rembrandt in the world and decide using every method they could whether it was real or not. And the project is still going. So, and they've redone Rembrandt studies completely. It was a major effort in what's now called technical art history. So, but basically what you do is you have the X-ray film, and you put it on a light box, and you get a little magnifying set that you put on your head, and you walk right up to the X-ray, and you go 1, 2, 3. Oh, the thing has a little square that has marks on it, maybe an inch or something. 1, 2, 3, 4, 5. And then you write it down on a piece of paper. Okay, and it fails every scientific test, right? It can't be repeated because you can't mark on the film X-ray. Okay, you're going to only do it for a couple of points, so statistically it's completely meaningless unless it's the thread count is totally uniform everywhere, which it isn't. And yet they were using these statistics. So to me, it was obvious that just inserting the computer, it's a problem they want to do, inserting the computer is going to help. So I'm going to quote a couple of things from literature around this time. The only way to compare canvas with a linen weave, that's that simple weave, is to measure the number of threads per centimeter in the warp and the weft. And those of you that haven't done weaving before, if you think of a loom, the warp is the long direction and the weft is the back and forth. We do this all the time. Every field does this. You have common terms and you define them with something else that nobody understands what the words mean, and that keeps out all the interlopers, right? So warp and weft. If the average number of warp threads per centimeter differs by more than one thread, one can practically discount the canvas in question coming from the same bolted part. Ernst von der Bettering, probably one of the 2 humans in the world that's counted more threads than anybody else. A real expert in this field. He's a very interesting fellow. So here's the one that did me now. Remember, I'm working with the Van Gogh Museum, and they said, we're going to count threads. I said, oh, yeah, well, huh? And they showed me an X-ray and this kind of stuff. And then they said, go read this. So there was a study done for an exhibition around 2000. Van Gogh and Gogh were together for 2.5 months in southern France. And they painted, and we have information from their letters that said that, I'll show you the nice picture while I'm talking. The information from Van Gogh's letters that said, I need canvas, I need canvas. He was always sending notes to his brother saying, I'm out, right? Now, how many of you have siblings? Okay? So you're always kind of overdoing it, right? If you want to get the recalcitrant brother or sister to do something. And at first, I think they believed all these letters were accurate, but now we've discovered that he's actually asking for canvas, and he had some that he was painting later that he already had. And what he's saying is, I've already planned what I'm going to do with all the canvas. So effectively, it's all used up. Please send me more. So then we get another note that says, it's okay. Gogh arrived and he brought a 20-meter roll of jute. Jute is the coarsest material you can paint on. It's about 6 threads per centimeter. Typical artist canvas is about 15 to 20. So they painted on this. Vincent hated it. He never painted on this coarser canvas again in his life. And basically, he painted things like this. And it turns out that he has a brush with lots of paint on it, heavily loaded brush. He's trying to pull it across a surface that's rougher than he's used to. And he has to strike the surface more times so the brushwork does not look like Vincent's normal brushwork, and the painting is de-attributed.
De-attributed?
Well, I mean, it started out with an F number by the very first guy that put the catalog together, but then the other experts came in and said, no way. Okay.
Well, F means it's the real deal.
F means De La Faille, this French fellow, put together the first catalog, and that's where most of the numbers come from. But yes, I would say 10 to 15% of the ones he picked are no longer considered Van Gogh. So it's always the big battle with the early 20th century. People wanted to include everything. And so since then, a lot of what's been done is kind of wheedling things down. So basically what happened was they studied the average thread count of these paintings, and they thought were from this period. They got them all. And they counted them all, and they figured out which orientation they went in, and then they lined them up 20 meters. So that meant that everything that they'd found was by one of the two of them. And so paintings like the one I showed you are now by Van Gogh, where before they were questioned. So this was a big deal to me. So this says, look, they can really use this for something. This is a freak. This was the only time he painted on canvas this course. So anything with that thread count, you can assume came from that one roll. Whereas in fact, there's a lot of paintings he does on canvas rolls that have about the same average thread count. So they got lucky in this case. They were able to say these were all by Vincent. So anyway, that was the background. So what I want to do is reduce the time humans take, provide some documentation, count a few more spots so everything's statistically meaningful, and then my hope is that I'm going to see something weird. Okay? Something weird that goes from one canvas through the whole canvas and goes across several paintings, so I can connect them. Some fault. I don't know what I'm looking for, but I just expect that there's going to be something that I can see that moves between them. There are things like double thread faults and a few other things that I expected maybe to find. Initially, we were looking at Van Gogh because of my connection to the Van Gogh Museum, and then also Vermeer. It turns out that we've actually collected all the x-rays of all the Vermeers in the world. I don't think anybody's ever tried to do that. So we finished that last year, and so we're looking at Vermeer. We've done several others. Those are the two big ones. And we're going to be like mathematicians. We're going to make some assumptions to make the problem easy, right? So I'm going to assume the threads are periodic. They're not. Okay? It's a lie. I'm going to assume the interference is additive. That's probably true. Most of it is, okay, because of the way the X-ray works. And that most of the interference is out of band. Also not true. There will be sometimes when it's in band, but mostly it is out of band.
Can you explain what you're talking about there?
Oh, sorry.
Interference between what, and what do you mean out of band?
Okay, the thread space out. Okay, so the thread count is at a pretty tight frequency range in all the possible frequencies. Okay, so we're just going to look in that little range, and we're going to effectively imagine that we're going to do a frequency domain type of analysis, and the big peak in that little range is going to be the thread count. Mm-hmm. Okay, and that can work if the thread spacings are periodic. Mm-hmm. And if the interference from everything else is additive, and it actually doesn't sit in that range so much, it's sitting somewhere else. So brush strokes are very low frequency. Some of the other faults you'll see, there sometimes can be nails and other metal that's in the wooden frame that shows up in the X-ray. Okay. There can be contrast differences where there's a stretcher bar in the X-ray. It attenuates the X-ray as well, so there'll be contrast changes. The X-rays will look pretty crazy. I'll show you in a few. Okay. So what you suspect right away then, I mean, the temptation is this. If I told you I'm looking for something periodic, what are you going to use? Fourier transform. I mean, that's the first thing everybody would think of, right? So that's what we're going to use, the simplest thing you can think of. How do we know it's working? Oh, we're mathematicians. We do this great. We know when we've got the Fourier transform, right? That's not the question I asked. How do we know that what the Fourier transform gives you is actually the thread count you see? It's only going to be true, perhaps, if it's periodic. It's a little bit not periodic. And if you look in here, you can see some places where we have really thin threads and some places where we have fat threads. So it's not like they're uniformly periodic. So the other side of it is, in order to say whether or not it's working, we've got to have some hand counts. We've got to know the truth, so to speak. So one of the first bits of software we wrote were things to help the conservators do the counts they normally did, not with the computer. So here's one where you see a little 2 centimeter square. You draw this line and then you mark where every thread is crossing, and it does all the statistics of thread spacing and thread count and so on and so forth. And this takes a minute or two, and this is a hell of a lot faster than what they did before. But the big advantage is I did take a screenshot, really low tech here. I take a screenshot of this when it's done, and I make a report. It's got all the statistics. I know where I took the counts. They can be repeated. They can be, tested. And I have a document. And if I can get all the museums to use something like this, they'll have data that they can actually swap with each other. Okay, so we use that. This is where undergraduates come in to the story. We actually counted 1,000 spots on 30-something paintings. And undergraduates will do almost anything for a grade, right? So what I did was I have the spot counted, and then another student had to count the same place until they agreed. So we had 1,000 verified spots, and we had, 6 teams when we started trying to do this different ways. And so we gave them this data set as the test of how accurate they were.
Were they allowed to communicate?
Sorry?
Were they allowed to communicate?
Who?
The two undergrads counting
Yes.
the same spot?
Yes. They were allowed to communicate after they discovered they didn't get the same answer. Okay.
We're all thinking they're just agreeing to.
Yes, I understand, but that wasn't the case. Okay, they had to bring stuff and present reports, so everything's documented. Anybody could look at what they've done. It turns out there's a few mistakes that are commonly made when you're counting, and some people just don't get it right the first time. Okay, it's not that hard actually. You can look in a few seconds at something like that and make sure everything's marked. Then there's no calculating. The other methods we used, you actually had to count, which meant that somebody had to actually check that. I didn't get the feeling that they were saying okay just so that they didn't have to explain. Okay, so it was more a matter if they knew somebody else was going to be looking. So anyway, we did this for this particular example I showed you. Take 17 spots and average them, I get this. Then I take a two-dimensional Fourier transform. That's the tool we're going to use. Okay, and I did 1 centimeter squares across the whole thing, so I had 3,500 spots. Pretty good, huh? So this makes me believe. So I did this, one like this with a one-dimensional Fourier transform. Actually, really the crudest thing I can think of. The first day the museum showed me the X-ray, I said, "Give me the data. I'll to be back tomorrow." So I went back the next day and said, "Okay, we'll count everything in the museum." They just couldn't. They just were laughing, because to do this by hand is like 10,000 man-year project. Okay, wow. So they said, "Okay, fine. We'll give you 30 paintings to start with, and we'll talk to you later." Because their interaction previously with people was they started doing cool stuff, and they got so interested in it they never came back to the museum. Okay, and so they don't have a lot of positive experience interacting with people on a collaborative basis. They have experience with saying, "You can draw a spectrograph for me. Draw it for this." Fine, thank you. We're finished. But to do collaborative research, there's this barrier you have to breach. So I said, fine, give me the 30. We've since counted everything in the museum. We've done weave maps of all their Van Goghs and about 150 others. So they are so convinced that we're on the verge of trying to make an international appeal, and maybe we can count them all. And I'll show you what we can do with it. But it doesn't work for everything. Rembrandt's a cheapskate. His canvas is actually fairly irregular threads, and Fourier transform doesn't work. So there's still plenty of room for doing better and improved thread counts here. My whole idea was to use the simplest possible thing that worked often enough to convince everybody that it was worth doing, and then step back. And the other thing is provide you with data, then step back and let smarter people than me take care of it. So here's an example. I like to show some art, right? So here's the X-ray, which has been composited from, it's normally taken in X-rays about chest X-ray size. This, I think, is 6 X-rays. Put together, I have the world's best stitcher, a fellow named Rob Erdman. It's hard to see where the overlaps are. So we take that X-ray and we do the thread count everywhere. And I'm sorry, if I could show you this colors here look a little prettier. This looks like not so pleasant, but what do you see that I see? I see stripes. So what we did was we went in and every square centimeter, we counted the threads of the Fourier transform, and then we put colors on them instead of numbers. Giving the art historians pages of numbers or matrices is useless. But if you show them color pictures, they get it. Just like you're getting it right now. I don't have to show you any numbers. So we chose the yellows to be kind of in the middle, and then the blues were low and the reds were high. So you can see that there's some places where the thread count's a little higher or lower than average in this direction. But here they're all similar, but you see very nice. This is the warp, and this is the weft. It turns out that the increased variance is a feature of the weft. So it becomes easy to see. But the thing that jumps out at me is that if there's stripes, imagine that this was painting 1, and this was painting 2. And I'd done them separately, done these maps, and now I can take them and do this really tough mathematical problem, correlation, okay, and find out which ones match each other. Or better yet, you don't go to the art historian and say, here's the answer, don't ask me any questions about how I got it. What you do is you go to them because they don't want to be removed from the object. They don't want to be removed from making the decision. You hand them 5 choices, and you say, we think some of these are good matches. What do you think? And of course they'll pick the right one. Okay. So again, if you go in and say, don't ask me, or wait, I did it better, here's a new answer, they quit listening to you immediately. They just don't think that way. So, okay, maybe this will match with something. So it turns out this was our first match. This is the painting that I showed you. This is another one that was considered a fake because there were 2 versions. One's in Germany, one's at the Van Gogh Museum, and there's only one mentioned in the letters. Okay, so that doesn't mean anything. He didn't say, today I didn't paint puppies and kittens. So, this is the problem with letters. They've not a full record of everything. These are these 2 paintings. And the Van Gogh Museum people had studied these endlessly and decided that they were made at the same time, had the same materials, and they thought the canvas looked similar. So this is one of the first ones they gave us as a potential pair. Well, it turns out you can start putting whole rolls together.
Wow.
So this is the front end of a roll. This is fine, and you can see here's 3 repeats of La Grosseuse, which he painted 7 times, I think. This is she's the lady that rocks the cradle. You can see this cord there. There's a cradle out of sight, and she pulls. It's a very typical way for rocking the cradle. You pull the string, and the cradle rocks. And she was a neighbor friend. And he actually has something in his letters about making a triptych with one of these in the center and 2 sunflowers on either side. So these were all painted at about the same time, it turns out. This is one of the sunflowers with the yellow background, blue background. And you can see this is the weft direction, which is coarser than the warp direction. Pretty cool, huh? They all line up. This one was misdated, so it came from another period, so it got redated. The point is that we have 40-something rolls that we've partially laid out like this. This should allow us to date his painting to within a 3-week period, because he went through each roll in about 3 weeks to a month.
Are the black spots like where you have an appearance that you put down?
Yes, that's exactly right. Thank you. I should have said that. So instead of trying to guess or interpolate or anything like that, wherever the surface paint is so obliterating, we'll just, if we don't trust it, we'll just put in black spots.
And what do you do some numerical thing to solve the alignment problem, or is it so clear you just do it by eye?
No, we actually, what we do, like with these, is we'll just take an average, take the addition across this way, and have a one-dimensional profile, and then we match those up. So it's all done with correlation, and then we look at them. Okay. The problem is that sometimes it's hard to tell which one goes where.
Yeah.
Okay, and there's other things that can be done. There's a lot that, unfortunately, I'm probably going too slow as it is. There's a lot that I'm not telling you, but you can also see the thread angle too. And so when it was stretched, there's cusping, so you can use a lot of other features to help you put them on rolls. It's a relatively unresolved problem. We don't have a good strategy. It's a puzzle problem.
Yeah.
Okay, but very, very cool. Here's, it's hard to see with the colors here, that these match up. You can think of this as a little darker going across here, lighter and stuff. This is in the weft direction, and therefore it's more coarse. These are very small paintings. This is until a few weeks ago, the only privately owned Vermeer in the world, and a lot of Vermeer experts hate it. They think the hands look like potatoes, and that the shawl is ugly, and the shawl may in fact be overpainted by someone else later. This is the lace maker in the Louvre, well documented Van Gogh that was in the family collection. So I'd read a study. I like to read the art history literature. There's a study of this painting. The last time it sold privately, actually, a big study was done, and there's this paragraph that says, boy, the canvas of these 2 looks a lot alike. So I got, excuse me for a second here. So I did this work with a fellow named Walter Liedtke at the Met, who's one of the 2 top Vermeer experts in the world. And 2 weeks ago, he was one of the people that died in that train accident in New York. So it's been a really weird 2 weeks for me. So Walter's prestige allowed us to get these other Vermeers. We got the one that was from the private owner, and we matched them up. And I remember talking to the head of the Van Gogh Museum, who's actually a 17th century expert. And I said to him, hey, we did some canvas matching with the Vermeers, and we matched up this painting, which everybody knows, with the lace maker. And his professional reaction was, shit. So he was one of the non-believers. Okay. So, so he gave the canvas to his cousin. His cousin sold it to somebody else, and they imitated a Vermeer. And, it's not like this is the final piece of evidence. It goes with everything else. It's just another piece of forensic data that the detective has put in front of you, trying to help you solve the mystery. But what's interesting is when we started this, how many paintings do you think were painted in the Netherlands in the 17th century? 250,000 probably would be a really low estimate. Okay, there was an explosion of art for this middle class that emerged. It was the first country that was not ruled by royalty, that had a large middle class, that had money. So everybody had paintings. So the expert at the Rijksmuseum for the head of collections said, "Oh, this sounds like a great project, but you're never going to find any Vermeers that match. He only painted 34 on canvases in an entire career." So there's one match. Here's another one. Okay, so these two actually happen to be in the National Gallery in London. So Walter, whom I mentioned a minute ago, believes them to be a pendant pair, meaning they were meant to be hung together and displayed together. Okay, and his theme is that one of them's the good girl and one of them's the bad girl, and this is loaded with all this moral lesson that any 17th century Dutch person would have known how to interpret. And we have a little clue, because in this one, the picture on the wall is Cupid, and in this one, it's a known Babura, and it's a brothel. So now you tell me which one you think is the good girl and bad girl, right? So Walter's assumed they should be together, and Arthur Wheelock, who spoke on campus actually just a few weeks ago, who's the other top Vermeer expert in the world, said, no way. Okay, so even after they were shown, these match up very convincingly. You can see all the major features are there, and there's strong belief that they're on the same canvas. What that means now becomes debatable. This one's even more interesting, because these two were painted 6 to 8 years apart. Everybody agrees. Well, what's he doing with his canvas? Oh, I like this canvas. I think I'll save the other part of it for 6 years. The problem is we don't have any data about his studio practice. So you can see where these things can tell you something about dating, attribution, in artist intent, and so on and so forth. Here's one that I really like, and then I have to get on to the other two topics. I'm telling you more about the painting because that's the project that's the most complete. These are in the National Gallery in London also. It's a triptych, a set of paintings, a suite of paintings painted by Poussin, turn of the century, 17th century, right around the 1700s. A French classicist who resided in Rome. Painted these for Richelieu in Paris. They became famous as a set, and years later, many repeats were made by Poussin's studio. This is the only one. It's in the National Gallery in London. It's the only one that's autographed, meaning painted by Poussin himself. This one's in Kansas City. It's thought to be maybe by a bunch of students or something like that, but it's not Poussin. The brushwork's just not good enough. And this one is in the basement of the National Gallery in London because it's declared an 18th century fake. Really terrible thing. They don't even want anybody to see it. So the Kansas City people said, we think ours is the real one. So they asked for the x-ray. I think you'll agree those two look like they match, right? And then they finally got the third one. Okay? So they took this data to the National Gallery of London, and this is what's great about museums. The curator looked at it and said, well, that's an issue for the next curator. Because just making these kinds of attribution decisions are really, really fraught. There's just an enormous range of information that has to be brought to bear. So that's been a lot of fun. So you can read more. There's a paper that tells you all about the signal processing stuff we did. And here's the most important thing. If you want to play along, you can't make your own thread counting routines unless you have real data. So I finally convinced the owners of the data we have 4 Vermeers and 6 Van Goghs on this website, and have at it. You can build your own algorithm. My hope is that you'll make one that's 100 times better than anything we've done, because there's just an enormous range of things to do. And I could sit here for the next half hour telling you all the different stuff you could do. So photographic paper. These are two pieces of photographic paper where what you've done is you've gone into the part that's either pale in the photo or it's an undeveloped piece of paper. And you've taken a shot that's, I think, 1.5 centimeters this way and 1 centimeter this way or something like that. It's a raking light shot, so you're shooting through a microscope and you have a raking light coming in at about 20 degrees. And we're humans, we can see the difference. Okay, why is there a difference? Is this an accident? Well, no, it turns out that photographic paper is made for its texture. They're all competing because the texture of the paper will affect the way the print looks. So artists, photographers chose the papers because of the effect they had. Manufacturers made the paper to gain these different effects, and therefore each of their brands has a specific surface finish. So the question is this: how can we find paper that came out of the same box or was made to the same specifications? Because if you imagine the artist making prints all in one go, they're coming out of the same box, and then you can establish that we're... Okay, well, it turns out if you look in the literature, there are people there saying, well, surface texture ought to do it.
Yes.
Okay? And so here's a couple of quotes. And so fine, surface texture. Geez, this is a classic surface texture problem. There must be 10,000 texture comparison algorithms. So the idea is to collect a killer set of data and then go out and invite people to come along and test them with their favorite algorithm. So that's what we did. But to tell you why this matters, I just hit a little bit. I got to show you some art. This is a Duchamp sculpture that's in the Philadelphia Art Museum. And it turns out this was done early in the 20th century when photography was coming along, and Duchamp was visited by Man Ray, who was one of the early famous American photographers, and he took the picture at the top of that sculpture. It looks just like it, doesn't it? Now, what he did was he went to the sculpture, which was glass, and stuck his camera and looked down the gap of the glass and saw the dust sitting on the glass surface. That's what you see. And this is an incredibly famous photograph because it was so early and so artsy. And I don't get it either, but that's not the point. Okay. So this one comes on the market. And it's not identical. You can tell right away it's not identical. But it's clearly the same photo. And the price for this one? $500,000. And so the person wanting to buy this contacts a colleague of mine who's actually the paper specialist I've been working with and says, should I buy it? Because if it's not by Man Ray, it's take off 2, 3 decimals. Okay, 2, 3 digits. Mm-hmm. And the answer was, well, let's look at the close-up, and by human eye, I'm going to decide that they're the same. So I looked at a similar spot on both photos, took this raking light thing. Do you think they're the same? I don't know, somebody spent $500,000 on somebody else telling them they were the same. So I'm thinking, okay, fine, maybe we can start doing some sort of texture similarity tests and somehow find which pieces of paper have the same, metadata, manufacturer, date, surface finish, style, that kind of stuff. So the idea is to automate all this from this giant library. It turns out the colleague we work with has been quietly buying old photographic paper on eBay for over 15 years. So he has a collection of several thousand pieces of undeveloped photographic paper, boxes of it. Okay, so there's our data set. We were working with MoMA. They also had a lot of data they could give us. So the idea, our hope is that by ranking the texture similarity, we'd actually group things according to their metadata. I mean, it's a real shot in the dark. There's no assurance this is going to work. Okay. Then the thing is we assemble this data set, this data set that was for unexposed, and so we assumed that texture was sufficient, and that not only that raking light images carried all the information we needed about the texture. We didn't need some sort of RTI or some sort of three-dimensional reconstruction. We're just taking a simple raking light photo. So we have 2 big leaps of faith here, in my opinion. So the project this far was just to try and show that if you went this path, it might work. So I'm going to ask you to be the computer. 2 of these match. Which are they? Now, what you're seeing here are these raking light photos I showed you, grayscaled, and then histogram equalized to emphasize the texture. But nothing's been moved. The scale's been emphasized. Do you really want me to tell you?
No.
Oh.
Not two you would have guessed.
Why 20 degrees?
Sorry?
Why 20 degrees to the angle of the light?
That's what gives you enough of the shadow because the height of the texture. So if you turn it up a little bit further, then you lose the shadow.
Okay.
If you put it too small, it's only shadow.
Okay.
So I didn't choose it. The paper experts were the ones that chose it.
And when you say that those two match, you mean what?
They're from the same piece of paper, different spots on the same piece of paper. Okay, so interesting thing in dealing with museums is what do they want to give you for data? If they're willing to give you data, which is the hardest thing to get out. I spent probably 85 to 90% of my time making nice with the museums, convincing them that it's okay to share data with me as an outsider. It's amazing how hard that's been. I had no idea that's where most of my time would go. What they want to give you are the ones they can't do. Geez, we have no idea where these photographs came from. We have no idea what papers are. Here, you tell us. So they don't get the idea that that's not where I've got to start. I've got to start with a big stack that they know exactly what they are. Okay, I just don't tell the computer that, and then I say, computer, find it. Or I can't do my Luke Picard volume. Computer, sort. Okay, and so off it goes, right? So the point is that what we need is a data set that's prepared with knowledge, and unfortunately, that's often what the museums don't have, because they're collecting the art object 100 years after it was created, and not the record. The records just aren't there for every art object. So from this data set that was collected by buying stuff on eBay, I finally convinced them. I said, I don't even believe that two spots from the same piece of paper are going to look the same. Convince me. So we ended up convincing them to take a really special set of data, 10 samples from one piece of paper. Okay? Then we took 10 sheets out of the same box and took one sample from each of those. And then we took 10 sheets from different boxes, but the same manufacturer specs. They might have been made at a different factory even, okay, or at a different date, but they were supposedly to the same specification. And then we took a fourth group of 10 that were just representative of everything else. And we did this 3 times. So we have a set of 120 samples. Okay, and so what we're going to do is try to see, the idea is the following. In that data set, when I compare them, anyone in this one group of 10 should match all the others. Right? Anyone in this group of 10 should match all the others. Assuming that there's none in here that match this one. And these may be also. These not. So that's what we're going to look for. We're going to look for the strongest match. We're not going to worry about the ranking of everything else. We don't know which ones are closer. I just know which ones I want to match up. And so here's 5 different teams. A 6th team has joined this project from the University of Michigan. And I just include some buzzwords about the different methods they used for extracting features and doing comparisons, just so you can see they're all different. And then we built affinity diagrams for them all, and they look like this. And basically, you can see 9 black boxes in each of these images. This is the experts' affinities, and these are the different schemes. So we take this to mean that there's something there. Clearly plenty to do. We've done the same thing for inkjet paper. We found a fellow in the Midwest that has a warehouse full of it, and it works there too. And we're now trying to do it for wove paper, which is one that there is no appreciable pattern at the scale, the visual scale. So it looks very random. But wove paper would be a big hit because that's what came in the late 18th century. And historical documents, manuscripts, all kinds of stuff are on wove paper. And it's right now there's no known method for comparing 2 pieces to be the same. There's a paper you can read with 21 authors, which is very unusual in the art history literature, in the Journal of the American Institute for Conservation, where we put forth this idea. And we have a website that's been established by the fellow that owns all these pieces of paper, okay, called papertextureid.org. And so there's 120 black and white or silver gelatin samples, and then there's 120 inkjet paper samples. And you're more than welcome to send him a note, get those, and try your favorite similarity scheme on them. There's heaps of work to do here. Anybody that's got a scheme, there's a zillion museums that have a lot of different projects, so this field could support dozens of different algorithms doing things. Okay, so How badly am I running out of time? It's supposed to be done already, right?
Well,
5 minutes?
you could do 5 minutes.
Okay, I'm gonna do this on super speed, which is not very good for me since I'm from the South. I don't talk that fast. Okay, what's that? That's called a beta radiograph. It's kind of a low energy X-ray of a piece of paper. It's a print by Rembrandt. Actually, it's not the whole print. It's just the part around the watermark. See this dude here? This is a jester's hat with the balls on the top. He has a 5-pointed collar. Okay, so this is a particular print by Rembrandt. Why am I not showing you this? Well, this is a piece of laid paper, and the laid paper has the frame, the mold, has wires going this way, and then a few, about every inch or so, going the other way. These are the ones that are about an inch apart. And so our idea is the following, and again, it comes from their own literature. I'm not making it up. Is that the sequence of these spacings, which are about an inch, but vary from about 0.85 to 1.2 or so, is that sequence of numbers will be unique to each individual frame. So the idea is to somehow see this image, extract those separations, and then build a big data set and compare them. And people have tried this before in an automatic sense, and either they assume the lines are straight and parallel, or they assume the lines aren't straight. And if they're not straight, it gets really ugly in a hurry trying to decide what the spacing is. So we decided to go after the space where nobody had been yet. We decided they were straight but not parallel. And it turns out they're not parallel, usually. So what that means is if they're not parallel, to line them up, you might have to move them this way to find where they came off of the bigger frame. So that's it. That's the only idea, is to look at that sequence. And here's a watermark in a frame. So what they do now is they identify paper by the watermarks. And you can't imagine how tedious that is, because if you had a cool watermark, somebody else is going to try to make one just like it in their paper, because if your paper is selling for a premium, then their paper will sell for a premium. So there's these watermarks that almost, they look just, you know, and you've got to look for hours, and then you spot this little difference. It's crazy. And I think trying to do that automatically is also completely over the top. Whereas finding a geometrical pattern is a whole lot easier. But we listen to what they say. Sheets with the same watermarks came from the same mold. Prints with identical watermarks must have been made around the same time. And so we can link their date and usage. So the problem with Rembrandt is that he printed prints. He was very mercenary. And a few years later, if he sold out of something and it looked like it was selling good, he'd make some more. Okay, but so they're not made, even though the etching has the date on it, that's not necessarily the date of the print. And you want to put them all in the right order. So what you do is you find all the ones that are on the same watermark on the same paper, and the one that has the latest date is the date of all of them. Okay, what's the problem? Only about a third of the prints have watermarks. Here's the big screen. I'm going to cut it into pieces, and here's the watermark. So only a couple of pieces of paper get the watermark on them. So we want something that does it without a watermark. So here's a quote from the bibliographic literature, not the art history literature, where they're studying things like, Shakespeare folios and stuff, and he was looking at popes. But yet here he says, the openings usually vary by as much as 10% and sometimes even 20%. That's those spacings. And patterns become evident when the measurements are arranged in a series. See, I told you I wasn't making this up. Then these patterns serve to identify paper molds. Now, imagine doing this by hand. That's why it hasn't happened yet. Okay? Here's the quote from the first people. There's a group in the Netherlands, the only group I could find, that has tried to do this automatically. And they got stuck because they insisted on everything being automatic. And right from the start, extracting the chain lines and everything. And Jan van der Lubbe has had 3 or 4 PhD students, the latest being Mark Staudunen, who worked on this. So we want to develop an automatic procedure. We want to reduce the number of things that might match to a smaller group. Remember, we're not trying to find the one. We're just trying to find a smaller group. We start with 10,000, and if I can lower it down to 20, they're happy. Okay? We're looking at Rembrandt first. We're assuming the chain line spaces here are unequal. That's true. And we're assuming the chain lines are straight. Bad, 90%. And not parallel. Probably 70%. So the idea is we got 2 weird P-cuts like this. They end up looking like that. And what we're going to do is line up the leftmost ones, put them in line with each other, and then move them apart until the lines form straight lines as much as possible, and that will tell us how far apart they are. And guess what? Finding this is a least squares problem. Once the angles are the same, it's a really trivial. It's very poorly conditioned, so you have to be careful. But it's there's no giant, huge mathematical leap here. It's not as trivial as it sounds to find them automatically. See, there's the chain line. This is a little bit of a blow up. You see the chain line anymore? So actually, it's not trivial to just go across and go, oh, well, that's where the intensity goes up. Okay, because these images aren't that high quality. But anyway, it's not as hard as that makes it sound. So what we did was, we again had students. We built a piece of software where they mark either end and then they mark somewhere in the middle that's the furthest off the straight line to ask if they're straight. And we decided that if they were if the box that bounded the line was less than 12 pixels wide, they were straight. And you can see that that's a large fraction of the ones we have. And straightness meaning that we would assume that if they matched, that they were the same pattern. We do have some that we know should match. And then we looked at parallel and picked the angle of about 0.12 degrees. If you're going to spread them apart, then the angle's a little bit different, then they get further and further apart. So the more spreading you can have, the smaller that angle has to be. If we set it around here, then there's a large fraction that aren't parallel. So we're the first people to look in that space, so it doesn't matter how dumb our solution is, it's better than any of the others, right? So then we looked at the spacings and what they look like. They're somewhat Gaussian. And then we noticed that within one sheet, the spacings are actually all close to the average, whereas the averages are spread across everywhere. And with these two things, we decided that if we had 4 chain spaces adjacent, that we would, and all the pieces had that, we'd be able to reduce the group down just by accidental matches down to 1% of the original start. So, and we have some procedure, not enough time. So here's what they look like. So these are the marked chain lines. These two are known to match. They're constructed by taking one and cutting it in half, and then treating it as 2 pieces. So we know that they should overlap. This is probably there's one that obviously doesn't. Okay. This is the interesting one. Here's one. Oh, by the way, you got to flip them, because when the paper was used, it might have been flipped this way or turned this way or turned that way. So there's 4 different flips you have to use. So here's 2 that match up. It turns out that these 2, this is the one I showed you originally. And if you look here, you can see the top of the fool's cap, the bell's on the top, right? But it's reversed. So we left-right flip this one, and then they match. And it turns out, we didn't know about the watermark. We did it just from the chain lines. Turns out that the owners didn't know they matched. The Morgan Library was the owner of these 2. But there's a book by Eric Hinterding, whom we're working with, and he pointed out that the fragments of the watermark matched. What's interesting is there are 21 variants of this particular watermark in his book, and each of them has subvariants. The one we're looking at, there's 9 subvariants. Okay, and one of those is ours, and it appears in 16 different prints. In other words, 16 different subjects. So ordering and collecting all these things, right now there's a 3-volume work that does it for the watermarks that was done by a human. No computer. It's unbelievable work, several years of effort. So what we're trying to do is extend it to a larger range. We think we'll be able to double what we can reach with this. So instead of 1/3, we should be able to do 2/3 of the prints. There's the 2 prints. So get a little bit of art at the end. And again, we have a paper that's to appear this July talking about the basics of this. And we've also put 129 of the betas from the Morgan Library and the Metropolitan on the same website of the RKD in the Netherlands. So if you want to play this game, or if you want to develop a method to find match watermarks, there's data you can actually use. Getting this data is absolutely non-trivial. And I think that ought to be enough. So I'll say thank you. There's 3 things. This is the beginning of, I think, a huge field. This is just a tiny little part where I'm looking at patterns and supports, but there's thousands of other things where computational will aid in answering art history and conservation questions. But the big deal, I think, is that part of what I wanted to do was to make this problem as open as possible and interesting as possible, but as open as possible by actually, instead of holding the data to myself and saying, I'm not done with it, 10 years from now I'll share it with you once I've done everything I can think of. The idea is to say, look, here it is right at the beginning. You can do better than me. What I've done for you is I've made the museums pay attention. I've made them share data. I've gotten a subgroup of other engineers, so there's a little group you can talk to that's interested in these things. So do it. Thank you.
we have some questions for Rick?
Yes, sir.
Back to the canvases.
Yes, sir.
You mentioned briefly at one point about angling of the thread.
Yeah.
Was that from stretching at the artist studio where they were cutting the roll to?
Unfortunately, it happens in lots of different places. Okay, so it depends on the artist, depends on the period. So I know most about Van Gogh, so I'll tell you a little bit about that. Van Gogh, the canvas was made by a person that just wove canvas. And those could be several hundred meters to a roll. It wasn't called a roll, it had some other name. Then those are cut into 50 or 100 meter sections and sent to another company that puts on the ground layer. So they'll take this 50 or 100 meter thing and put it on a big wooden frame that has nails on the top, and they put holes in the bottom and put a string through it. And so they pull on the string to tighten it. So it's sitting on this big frame that's 50 meters long, and it's more than 2 meters tall. Okay, and then they get out big brushes and they put the ground layer. This is the material that makes the canvas smooth. Okay, it's the thing that's radio opaque that shows up in our X-rays. Then they cut it down into smaller pieces and sell it to the colorman, the person who's actually selling supplies to the artist in different places. Okay, that's the way probably over half of Van Gogh's paintings reached him. The other way is to buy raw canvas. This is mostly what Vermeer did. He bought the canvas before anything was put on it, just bought the canvas, because in his period, canvas wasn't made for artists. It was made for anything else but that. It was made for sales and all kinds of other stuff. They'd buy the piece of canvas, and they'd put it right on the stretcher they were going to paint on, tack it on, and then start putting everything on it. Now, how can we tell? Because if I tack the canvas on and then put the ground on it, I'm not going to put it on the side. So there you saw that the ground layer only appeared on the part that was on the front face of the painting. And in Van Gogh's, the ground goes around all sides, and the paint's only on the top. So there's evidence you can infer from it. Okay, so now, back to your actual question. When you do this and you stretch it and you before you put the ground layer on it, you put glue on it, sizing. It's called, and that's to keep it from being absorbent. You know, if you've ever touched canvas, raw canvas with a liquid, it just. So the idea is to hit it with this animal glue that keeps it from absorbing the paint too rapidly, but it also stiffens it. And it's at that point that you freeze in the pattern of the stretching. So if it's done right on the stretcher, there'll be cusping on every side of the painting. If it's done on a bigger frame and then you cut a piece out of it, the cusping may only be on one side. Now, if you take the painting off to transport it, which Van Gogh did, and send it to his brother, he's going to put it back on another stretcher. Okay, and then whereas the primary stretching may be 10 to 20 centimeters in depth, the secondary cusping will probably only be 1 or 2 centimeters at most, and often you don't see it. Does that answer your question? So, I mean, this is the problem. You've got to know all this other stuff to how to interpret the data you see. I mean, this is why you can't come in as just a mathematician and say, here's the answer, and hand them the program and walk away, which is what's happened in the past. And guess what happens? It ends up in the drawer because they don't even know how to run it. Okay. Sorry, that was a long question, a long answer to a short question. So, anything else, or is everybody ready for something to drink?
Well, okay, so we can go next door and have some cookies and refreshments. Thank you very much.
Oh, sure.